Hello, this is the video presentation for Team 19046, the double-ended interferometer team, which was sponsored by Sandia National Labs. The team which worked on the project consisted of two optical engineers, Kian Milani and Nathan Gottesman, an electrical engineer and Jingxi Wu, a mechanical engineer and Nathan Klinicki, and myself, mechanical engineer and team lead Casey Thacker. Here's the poster which we would have used on design day. It introduces some of the important topics which we will discuss more in depth later in this video. The project was to design a double-ended interferometer specifically to measure the length of gauge blocks. The precision measurements of gauge blocks are used to calibrate and align other systems. Interferometric measurements are the most precise as they provide a direct relation to the speed of light from which the meter is defined. The primary standards lab at Sandia currently utilizes an interferometer which requires the gauge block to be rung onto an optical platen and has a maximum length capability of 100 millimeters. Interference between the optical platen, gauge block surface, and the reference mirror are used to extract the length of the gauge block. Our objective for this project is to design an interferometer which will take interferometric measurements from both ends of the gauge block such that the gauge block is not required to be rung onto a surface. We have the following design constraints. Firstly, the design is determined such that ringing onto a surface is not required. This would eliminate the uncertainty introduced by the thickness of the ringing grease. Also, we needed to measure a large range of gauge blocks, specifically 0.25 to 500 millimeters. The gauge block faces must also be profiled so that we are not measuring the length only at one specific point on the gauge block. Lastly, the system was to be controlled by a MATLAB GUI as requested by the sponsor, so all electronic components must be compatible with MATLAB. We took a four-step approach to our problem. Firstly, we conducted research in order to find references which describe interferometer systems that exclude ringing. Next, we developed ZMAX, MATLAB, and SolidWorks models of a system that integrated our final agreed-upon point design. After, we searched for specific parts and integrated them into our models as well as keeping the budget in mind, and we finally began integrating and testing parts we ordered as well as developing a necessary software system. Next, we will detail the research and design phase of the project. One of the first designs was found in a paper by Ishii. It detailed the equations used to calculate the length of the gauge block, involving the use of 3 interferograms for each position of the reference mirror. The extraction technique was to take interference data at many phase shifts, then fit the data to a sinusoid to extract the phase. The phase shifts were conducted by shifting an optical wedge across the face of the reference mirror. A drawback is this design used a single wavelength, which meant the initial length of the gauge block would already have to be known within lambda over 4 accuracy, because mathematically, the gauge block is represented as an integer number of wavelengths plus some fraction of wavelength, and this algorithm only solves for the fraction and not the whole number. Next, the Bukta design utilized a white light source with low coherence length to detect changes in intensity when the reference mirror was moved. The drawback to this design is that the reference mirror must be able to move the length of the gauge block. Translation devices with this large-scale range results in less accurate measurements for our system. Here, the Raoult design is somewhat similar to the Ishii design. However, it uses 2 CCDs and 2 reference mirrors such that light passing from one direction is used with light from one of the other 2 reference mirrors. Therefore, a drawback would be the cost of the system, as having 2 reference mirrors capable of being phase shifted drives the cost up very much. The final accepted design only needed one reference mirror with a low range of travel. This design would utilize a 2-wavelength laser which was provided by Sandia such that a synthetic wavelength could be created and the initial length estimate of the gauge block is not required to be lambda over 4. This system would utilize a beam expander and compressor so that the faces of the gauge blocks could be profiled. Unlike Ishii, a piezoelectric translation stage would be used to phase shift the light from the reference mirror. Instead of using a high sampling points, a 7-frame GRU algorithm would be used to extract the phase, as this algorithm has been shown to be more insensitive to phase shifting errors. Here we can see the overall system architecture, which consists of 7 subassemblies: the laser, camera, gauge block, reference mirror, interior optics, interferometer housing, and computer subassemblies.
Hello, I'm Nathan Gottesman, and I handle most of our simulations. If the underlying theory in our project had to be summarized as briefly as possible, these 3 equations and graphic would be it. The graphic shows all the possible paths light can take from the source to the detector. First, we extract the phase of the light in the 3 paths with the reference path. This is done with the 7-frame pi/2 phase shifting algorithm summarized in the top equation. This algorithm samples multiple frames over 2 periods. By doing so, some of the error due to environmental factors is averaged out. Using the phase of these 3 interferograms, an effective phase representing the length of the gauge block can be determined. This is summarized in the second equation. By comparing the phase of 2 close wavelengths, the actual length can be found by finding the phase of a synthetic wavelength. This is summarized by the bottom equation. The primary simulation built uses a plane wave approximation of our field to predict how different variables may affect our accuracy. These variables include a decenter of our gauge block using multiple source wavelengths, the spectral width of our source, and different extraction algorithms. Because of the source Sandia provided amidst 2 wavelengths along orthogonal polarizations, understanding how we could utilize the 2 wavelengths with a polarizing beam splitter was crucial in order to measure the length without an initial guess. By simulating the interferogram in 2 dimensions, we can simulate the effects of tilt and other aberrations on our measurement. Aberrations induced before and after the beams are split have negligible impact because they do not induce an optical path difference between the beams. Slight angular misalignment of the beams will not have a large impact on the accuracy of the measurement as seen in the figures above.
Case Thaka here again to discuss the part selection process. The interior optics were chosen with the necessity to profile gauge block faces in mind. 2-inch optics were decided upon because that range encompasses the face of every testable gauge block. Also, plate beam splitters were decided upon because they are cheaper than 2-inch cubic beam splitters, and even though these changes to the beam is elliptical, the beam still encompasses the face of the gauge blocks due to their aspect ratio. The posts which were chosen to mount much of the optics were 1.5 or 1 inch long posts, each being 1 inch in diameter. These were chosen to suppress as much of the noise introduced by mechanical vibrations as possible, while still raising the optics to an appropriate height. The beam expander and compressor were designed using ZMAX Optics Studios with stock lenses from vendors to be diffraction limited. They would expand the beam to the required amount to profile the faces, then compress them to fit the interferograms onto the camera detectors. The most common components used for temporal phase shifting are piezoelectric actuators. Due to our budget, we mounted our reference mirror atop a piezoelectric translation stage, which had a strain gauge attached, allowing for closed-loop operation and negating specific air types. Because the housing was not integral for the basic operation of the system and there were budgetary constraints, a complete structural enclosure was not designed for the system. The housing was to be constructed from cardboard, which would act as an insulator and block from stray light. There would also be slits in the cardboard, which would allow for manual operation of the beam blocks. Environmental sensors were necessary to characterize the environment in which each gauge block was being measured in. Sensors from Adafruit would be used in combination with an Arduino board to record readings of temperature, pressure, and humidity and translate that information to our GUI. The gauge block mount needed to be kinematic in order to account for the varying size blocks being measured, so custom adapters were designed to fit on an optical rail. Gauge pins and steel ball bearings were used to create a plan on which the gauge block would sit when being measured. Ballpoint set screws were used to fix the gauge block's angular position with respect to the incoming laser profile and acted as point contacts as well. The cameras decided upon were manufactured by Thor Labs and furnished from Sandia, allowing us to save on the budget. Utilizing 2 cameras allowed us to capture interferograms with both polarization states of the laser at the same time. Next, we will discuss the aspects of the software design. The software was designed such that it would allow the user to run through the process of taking a measurement. The actual process would consist of mounting the gauge block, starting the program, and manually adjusting beam blocks. The software would capture images, actively control the piezoelectric stage which shifted our reference mirror, and read data from the environmental sensors. Now we can discuss some of our initial assembly and testing. We tested the camera's dynamic range and also checked for dead pixels to ensure that the cameras would read accurately. Also, integration of the beam expander and compressor were tested in the system and found to have an insufficient control over the actual lenses which made up the subassemblies. The translation stage we purchased was also tested, giving us insight into the necessity of a strain gauge. Here we will discuss some of the setbacks the project faced. The original piezoelectric translation stage we ordered was not compatible with the strain gauge we had acquired, so we had to communicate with the manufacturer and determine within ourselves which type of changes needed to be made in order to have a compatible piezo. Also, COVID-19 really changed the whole scope of this project. The university and all related facilities shut down, meaning that we were not able to assemble, test, and align many of our components as we originally intended. The manufacturing of the mounting system was also stunted because all the student accessible machine shops closed on campus as well. As for deliverables, originally, a full-functioning double-ended interferometer was to be delivered to Sandia. Due to the previously mentioned setbacks, specifically COVID-19, we are sending Sandia all of the components as usual, including MATLAB scripts, SolidWorks files, and ZMAX models, as well as a document guiding the next senior design team or engineers who work on the project. It's integral that we outline all of the design choices we have made and what the next steps going forward are to ensure that the next group that works on this project is properly informed on how it is intended to be designed and used. Thank you all for listening. We would like to thank Sandia National Labs and our point of contact there, Wyatt Hodges. Also, we would like to thank James C. Wyatt, College of Optical Sciences, our mentor, Doug May, and the rest of the staff at the University of Arizona which helped us through our project. We hope you found this video informative and want to say thanks again. Bear down.